Okay, so again, please have your PC ready with Microsoft Excel. It's very basic. And then please download the materials for the tutorial in the Spectrum. And also I put there an Excel file for you to download. So please download that one also for our purpose in the tutorial after this. All right. So just to recall things that we have seen so far in this lecture 5. So lecture 5 deals with the modeling of behavior of materials, specifically on the nonlinear elastic materials. So this is a class of material response whereby the response of materials remain elastic, so you don't involve plastic deformations, yet the stress-strain relationship is not linear like in metal. So it is a nonlinear elastic material response, and then it is this kind of response, as I have mentioned many times in the last lecture, is shown by class of rubber materials, elastomers. Okay, and then in order for us as mechanical engineer to conduct a proper stress analysis for components involving rubber materials, we cannot use a conventional Hooke law in the stress analysis. Okay. It is not enough to only have informations on the elastic modulus and Poisson ratio to conduct three-dimensional stress analysis, like what we did in linear elastic for metallic materials. We need something else because the stress-strain response is not linear. We have seen that, okay? And then in order for us to derive the proper constitutive equations or materials model, mathematical model to describe stress-strain response of rubber. Okay, as usual, two different approaches can be followed: physical approach and then also phenomenological approach. As a reminder, in physical approach, in order for us to come up with the equation for the stress-strain, we need to look at the microstructure. Okay, and then we have learned that looking at quickly the microstructure, considering the thermodynamics of deformations, and then we come up with neo-Hookean model. Okay, and then we have seen that, and then we have conduct a simple stress analysis for uniaxial extensions of rubber band. And then also in the last sessions, we started the discussions on phenomenological approach. In this approach, there is no need for us to look at the microstructure. We just simply have to come up with a proper mathematical equations describing stress as a function of strain. And then in order to do so, because we are dealing with rubber, which is capable to undergo large strain, we need a theoretical framework to do this. And then continuum mechanics provide that. So we had looked at a very basic introductions of continuum mechanics, especially dealing with the various way how we can measure or quantify the deformation in the materials using various or different strain measurements. Okay, we have seen the introduction, a very brief, at least it is to introduce to you to get familiar with the concept because it will be used today. First is the deformation gradient tensor, and then we learn about the left and right Cauchy-Green tensor, and then we learn also Green-Lagrange tensors and other strain tensor measurement. Okay, so this tensor we have learned, and then we are going to use it today in the phenomenological approach. Again, in phenomenological approach, we are not going to look at the microstructure. We simply want to come up with the mathematical equation describing stress and strain without really looking at the microstructure, as long as it works, as long as it is capable to describe correctly the stress-strain behavior of the materials. So that's the whole idea of the phenomenological approach. Okay, so let me start by a simple definitions of hyperelastic materials. So this is a simple definitions. Many of the things that I showed to you directly coming from the framework of hyperelastic materials that I will not also go much into the detail because of the limitations of time. As long as I introduce to you and you know how to use it, And I would like to invite you to read books if you like to know more about certain concept that I introduced briefly here. Okay. So first, what is hyperelastic material? So this is really a concept basis, mathematical basis. Okay. So the idea is that what are hyperelastic materials? These are materials characterized by the existence of strain energy functions defined per unit volume in undeformed configurations whose stress response functions have physical expressions of the form as given there. So this is a mathematical concept definitions. So the idea, to make it easy, is that what is hyperelastic materials is that the stress-strain response can be obtained, the theoretical stress-strain response, the mathematical equation for the stress-strain response can be obtained from the informations of the strain energy functions W, where the stress is simply differentiations of strain energy with respect to the deformation. So in the proper way, it is said that P here, what is P? P is the engineering stress tensor, or something that we call commonly in continuum mechanics as the first Pila-Kirchhoff stress tensor. Okay, so the engineering stress tensor is simply the strain energy, which is a function of F. If you remember F, it is the deformation gradient tensor. Okay, so we need to write strain energy functions as a functions of F and then differentiate with F. So basically, stress is strain energy differentiated with respect to strain. What is the meaning of the two equations here? Wi equal to 0, Wf equal to 0, which means that I is identity tensor. The components, the diagonal components, if you remember in the last sessions, are 1, 1, 1. It's a matrix 1, 1, 1 in along the diagonal, and the rest outside diagonals are 0. Okay. When F is the deformation gradient, more than 0. And after that, what does the meaning equal to 0? It means that whenever W functions of I, it means that before the deformations, energy is defined as 0. As simple as that, the meaning of the first term here. While when we impose deformation, then energy is positive. There is no negative energy. Initially, we suppose energy is 0, and when it is deformed, it becomes positive. That's it. Okay. Now, so the whole idea now, meaning to say that if I look at back the stress-strain curve, the stress-strain diagram of rubber materials, for instance, this is the stress-strain diagrams, the experimental data is provided, is given by the circle, small circle here. Okay. The idea is that can we get the mathematical expressions for W such that when I differentiate with respect to strain, then I have a theoretical value of stress which fit best with the experimental data. That's the whole idea. I hope it is clear. If you have any questions, let me know. So the idea again, can we come up with the mathematical expressions describing stress and strain such that when we plot and compare with experimental data, it match best, it best fit. And then it start by finding the W. When we get the W, differentiate with respect to strain, we get the stress expressions, and then we plot the theoretical stress expression, compare with experiments, it has to fit well. That's the idea. Now, in that case, because the idea is to find W, mathematical expressions of W, can we give arbitrary W as long as the result fit with experiment? Well, the answer is no. Quick answer, okay? You have to respect certain principle, particularly these two principles. The first one is the principle of materials frame indifference. Okay. Second one is isotropy of materials. So these are mathematical terms. I'm not going to go into the detail, just to let you know that when we have W, we cannot simply choose it arbitrarily. We have to respect certain restrictions, and these are the two restrictions. Okay. So what are the consequences of these restrictions to the expressions of W? I will go just briefly to guide you to the next step before we come up to the final expressions of the mathematical equation for stress. Let's have a look first for the principle of materials frame indifference. What does it mean? So it means that The mathematical expressions for W must be unchanged during translation and rotations in the deformed configurations. Well, probably it is difficult to understand that, but the idea is that in order for us to fulfill these first restrictions, then W must be expressed as a function of C, the right Cauchy-Green tensor, the left Cauchy-Green tensor, C is the right Cauchy-Green tensor, B is the left Cauchy-Green tensor, or E is Green-Lagrange strength tensor. Okay, so instead of writing W as a function of F, like what we mentioned initially here, W must be expressed as a function of C or B or E to fulfill restriction 1. So that the stress tensors, I will not go into the detail how it is calculated. We can have now the engineering stress is this one, the true stress is this one. Just for your information up to this one. Yeah. Next, restriction 2. What does it mean? You have to fulfill isotropy of materials. So the mechanical response are the same in all directions. Okay. So we look at mathematical theory. Again, I'm not going to the detail, not to confuse you too much. But if we want to fulfill the restriction number 2, then instead of fulfilling expressing W as a function of C, B, and E as in the restriction 1, instead we need to express them as functions of invariance. Where are the invariants 1, 2, and 3 of C or of B? And then the previous expressions for the Cauchy stress or the true stress here become this one. How it is derived, you need to look at in the book. But at this stage, it is not necessary for us to understand the detailed derivation, how to come up with this one. Okay, noting that I1 equal to this one, I2 equal to this one, I3 equal to this one. Trace means that, remember, the sum of diagonal component. Okay, while det means that determinant of a matrix. All right, so this is when the things that I put in the box is something fundamental that you may need to refer when you do the calculations. So note that I1 can also be trace of B here. Okay, I2 can be also, this is trace B square minus trace B square here. On this one also determinants of B, it will be the same. Okay, either you use C or B, it is the same. So please remember this. Either you use C or B in the invariant, it is the same. So now, I have mentioned in the last class that rubber often deform at constant volume. So when we deform the materials, these materials will deform, but maintaining the volume, and this is called as incompressible. Okay, incompressible means that I3 equal to 1, so that the previous expression for stress change and to become this one. So this is the final stress strain equations for rubber materials showing nonlinear elastic material response. Okay, so this is the true stress. So sigma, the matrix of sigma equal to minus P. What is P here? P is Lagrange multiplier, which needs to be determined from the boundary conditions. How to do that? I'll give you example in the tutorial later, and also in the example here. Times I, matrix I, tensor I. What is it? As I mentioned, it is identity matrix. Okay, plus these two terms in the bracket, differentiations of W with respect to I1, because now W is expressed with respect to I1 or I2, plus I1. I1 is trace of B or trace of C. And then this is the next terms, and times B minus 2 differentiations of W with respect to I2 times B square. And then the engineering stress can be simply obtained from the true stress through this equation. So engineering stress is equal to true stress times the deformation gradient, inverse, and then transpose. How to do the operation? You can either transpose first and then inverse, or you do the inverse first and then transpose. It's something the same, something that you have learned in algebra of matrix. Okay, so which means that, look, now I have the framework. This is the general equation for rubber. How to find the definite expressions depend on W. So the idea is that we need to develop W as a functions of I1 and I2. So if we know what is W as functions of I1 or I2, and we can make differentiation, then we get the stress. So now the challenge, what are the mathematical expressions for W? Because we need to specify it. So a lot of form or expressions of W are available in the literature, many. Okay, for instance, Neo-Hookean. Neo-Hookean, actually, if you look back, we can also see Neo-Hookean as a strain energy functions, which has the form C here, C1 times I1 minus 3. What is I1? I1 is actually lambda 1 square plus lambda 2 square plus lambda 3 square. Something, if you look back in the Neo-Hookean, in the physical approach, and C1 is actually the one that we have before. It is, if I remember correctly, it is G over 2, yeah, and KT. So look back operations, and then we can have Mooney model. So if you see Neo-Hookean is only a functions of I1. So we can choose whether it is a function of I1 only or I1 and I2, but you cannot have a functions of I2 only. Yeah. So here, for instance, Mooney proposed in 1940 that this is the W, according to him. Again, people propose differently, and then we need to check whether it works or not by investigating one by one. Okay, and this is the most common things that you can find in the literature. This is the general Mooney-Rivlin. So this is a series, only C1, C2, but you can have a lot of series to get a better precision of the result. And then, for instance, you can have also Biederman model, which is given by this one. Okay, so this is the expressions of W. So which means that this W, you can choose whichever you would like to use, and then you put back here. Okay, and then we will do the example how to do that. We can also have different way, Hart-Smith. So this is just to let you know. Ogden model, Yeo model, it is very famous. Yeo models is very simple yet quite accurate in predicting correctly the mathematical equations and his relations. Okay, so it's very well known. I like this model, Yeo model. It's simple yet capable to predict well the behavior of rubber. Okay, so let me know if you have a questions, okay? Because this is very important, this part. You can type in the chat box. You can just interrupt me if you have a questions. Let's see how to use it here. This will be also part of your tutorial in the next part. Okay, now I have this example 6. A rectangular rubber band is subjected to a simple uniaxial tensile loading. If rubber is assumed to be incompressible as usual and isotropic, determine the non-zero components of the Cauchy and first Viola-Kirchhoff stress tensor. Okay, so you have here rubber band. Let's say that it is stretched along direction 1, along the length, and the length is along direction 1, such that the length change become from L0 become L. The deformation gradient for this case is given. Okay, so in many cases, okay, if I ask questions, for instance, in exam, I will give you the expressions of F. Okay, and then from F, then you have to work out things. This is F, and then you know that if this is F, you can get B. B, if you remember, it is F, FT transpose. So you look at here, this is B, for instance, and then lambda is L over L0. So this is something that we have learned before. And then what is I1? I1 is either you put it trace C or trace B. What is trace B? This is lambda square plus 1 over lambda plus 1 over lambda. So you look back there. Okay. And then the engineering stress is the true stress times deformation gradient, inverse, and transpose. All right. So what to do next? Well, these are the equations that we have. Okay. And then the idea is how to link between stress and strain for this particular case of uniaxial extension. So I have the 3 equations, and then I will just then put it in the matrix form, the first one. this one. Okay, for this one, let's put it in matrix form to make it easier to understand. This one. Because it is uniaxial extensions, then there will be no shear stress. It is only axial stress, normal stress. Okay, so this is the matrix of sigma. So the components, shear component will be 0. And then we only have normal components, sigma 11, sigma 22, and sigma 33. But you know that since we load the materials only along direction 1, we know that there will be no stress, normal stress along direction 2 and direction 3, which means that sigma 22 and sigma 33 are actually also 0 because we only stretch along direction 1. So there is only sigma 11, which is non-zero. Okay, next P. Okay, P times matrix I here. Okay, I is matrix 1, 1, 1 here. The rest are 0, and then multiply by minus P, so it becomes minus P here, minus P here, and minus P here. All right, plus, well, I leave the terms here, okay, and I haven't replaced I1 here, okay. You know that I1 is the trace of B, okay. Where is B? This is B, matrix B. Okay, and the trace of B or I1 is simply lambda square plus lambda minus 1 plus lambda minus 1 there. Okay, but I haven't put it here. Okay. Plus, well, or minus the last terms, 2 times this one, I leave it this one, and then you insert B square. You do just simply multiplications, matrix B, and you get that one. Okay, I will go back in detail in the tutorial, but the idea is that now, okay, how to read this equation? It means that sigma 11, now if I take out only sigma 11 equal to minus P plus these terms, 2 times the terms in the bracket, times lambda 2, lambda square, so only this component, minus the product between 2, this one, times lambda 4. So this is, I take out lambda 1. So lambda 1 again is simply minus P plus 2 times the terms in the brackets times lambda square minus these terms times lambda to the power of 4. In the same way, sigma 22 or sigma 33 or sigma 22 equal to minus P plus 2 times these terms times lambda minus 1 minus these terms times lambda minus 2. So if you want to take out one by one, so you know that you have to relate between the corresponding components. Okay. All right. Something that you notice is that sigma 22 and sigma 33 are equal, as you can see here. Okay. As you can see here, this is the particular case of uniaxial extensions. For other case, that is not true. Okay. All right. So we know also that sigma 22 equal to 0, sigma 33 equal to 0 because it is uniaxial extensions along directions 1, 1 only. Right? So which means now, if I need to focus only on sigma 1, 1 because this is the only non-zero component of stress. Okay, so sigma 1, 1 equal to minus P plus these terms lambda square minus these terms lambda to the power of 4. So in order for me to know sigma 1, 1, I need to know what is P, which I don't know yet. How to do this? I can know it if I already choose which W that I will use from the previous list that I have shown to you. Okay, so W, if I choose certain specific W, then I can differentiate directly, no problem. Okay, how about B? B, I know as long as I impose that, for instance, by how much amount of lambda I would like to stretch the materials, then I can immediately get the answer for sigma 1, 1. Okay, so for instance, what is the amount of stress when lambda equal to 2? When lambda, if I stretch the material 2 times, if I stretch the materials 3 times, for instance, I can immediately get the answer of sigma 1, 1, provided that I know P. So I don't know P yet. I have to find what is P. How to find P? P, as I mentioned, is the Lagrange multiplier that needs to be determined from boundary conditions. So what is the boundary conditions that we have here? Well, we have information that sigma 22 or sigma 33 equal to 0. So we can get the value of sigma minus P here from the second relationship here, this one. Boundary conditions state that sigma 22 equals sigma 33 equal to 0. So if I insert these equations and consider, for instance, only component 22, component 22, component 22 here, then I can easily deduce that P equal to this one. Now with these informations of P, I can put back to the first equations to get sigma 11. So that after a number of mathematical manipulations, I get that sigma 11 equal to this, P11 engineering stress equal to this one. But sigma 11 is force over actual cross sections, engineering stress is force over initial cross sections, and I have these terms. Which means that if I choose or select what is W, I can immediately get the answer for sigma 11. Okay, in order for me to move from this stage to the get final answer, there are a number of mathematical manipulations needed. Okay, and I will show you in detail how to do it in the tutorial next. Okay, how to come up with these equations. All right, so this is the final equations for the stress strain of hyperelastic materials subjected to uniaxial loading conditions. So the final expressions will depend on what W that you choose from the list that we have before. Okay, and then let's have a practice in the next example. Let's say that I want to choose Neo-Hookean and Mooney hyperelastic model. What will be the expressions of the true stress that I have? It's very easy. For Neo-Hookean model, this is the expressions of W. It depends only on I1. It does not depend on I2. So if I insert here, I know that the second terms will vanish because it does not depend on I2. So sigma 11 reduces to these simple equations according to Neo-Hookean model. So this is theoretical prediction. Do not confuse why they are different and which one is correct. Well, it's different models give different result, gives different predictions. Some of them will be accurate, some of them will be less accurate. It's a matter of choice. Like when we did for physical approach, if you remember correctly, with Neo-Hookean, it is simple, but you can only use it for a rubber subjected to, well, small up to moderate strain level. If the rubber is subjected to higher strain level, then you need a more sophisticated model. For instance, Aruda-Boyce model or 8-chain model that we discussed. Yeah. For this one, I want to compare between Neo-Hookean and Mooney. Well, for Neo-Hookean, this is the mathematical equations. How about for Mooney models? For Mooney models, according to Mooney models, W depends on both I1 and I2. So if I insert this W to this equation, then I get the expression from sigma 11 equal to this one. So as you can see, the final expressions will be different. Okay, if you use Neo-Hookean, then your model contain this parameter C1. If you use Mooney model, then it contains parameter C1 and C2. What are the C1 and C2? Do they have any physical meaning? The answer is no, because it is phenomenological approach. They are just a constant of parameters related to material that are there simply to ensure that your result will fit with the experiment. It does not have any physical meaning. It's just mathematical constant. Okay. Of course, different materials will have different constant, but these constants cannot be related to any physics of the materials. Again, it is physical approach. So I hope this is clear for all of you. Okay. So finally, if you are using Neo-Hookean, then this is the final expressions for the stress. If Muni, this is the final expression for the stress. So how to get C1 and in the case Nihokien, or how to get C1 and C2 in the case of Moni model, you need to look at the experimental data. You need to fit from the experimental data, which means that you need to identify from the experiments what are the value of C1 and C2. There's when experiments are still needed to identify the behavior of the materials. So as a remark, the parameters appear in the materials model depend on the specific type of rubber considered in the study. Their values can be obtained by fitting the experimental stress strain curve. Okay, I think this is the last part. So we have discussed for nonlinear elastic materials, 5.1, 5.2, 5.3. And then I'm open to discussions now before I continue with the tutorial exercise that we are going to do together. Any questions so far?
I have a question, Doctor.
Yes, sure. Go ahead.
So earlier on, you said that the boundary condition for sigma 22 and sigma 33 is 0. How do you get that? I lost in that.
All right, sure. Okay, let me go back here. That's a very good question. How come sigma 22, sigma 33 equal to 0? Now, imagine that you are doing stretching tensile test. You did it in the first year. You stretch it vertically, only along one direction. When you plot stress strain curve, you calculate the stress. It is the stress along direction of stretching. Is there any stress along direction perpendicular to the stretching?
Supposedly no.
No, because direction 2, so direction 1 will elongate it, gets longer. Direction 2 and direction 3, which are the lateral directions, will contract freely. And then when it contract freely, there is no stress. So sigma 22 and sigma 33 equal to 0.
Okay, Doctor.
Is that answering your question? If it is still not clear, please let me know. Yeah, Adi?
Okay, Doctor.
Clear?
Yeah, clear.
Any other question, please? So this is the boundary condition for uniaxial extensions. If you stretch it along direction 1, then the stress along direction 2 and along direction 3 are 0. But let's say this is hypothetical case. Please take note because this is very, very important. You may want to repeat again this video. Okay. Here the example is only for uniaxial extensions. What happens if, for instance, I stretch simultaneously along direction 1 and along direction 2? Well, along direction 1, the material will get longer. Along direction 2, the material also will get longer. But along direction 3, there is no stress. The material will contract freely. So in this situation, there will be stress sigma 11. There will be stress sigma 22. But there will be no stress in sigma 33 because in direction 3, it is free to contract, no resistance. Okay. In this situation, the boundary conditions that you will need to use is that sigma 33 equal to 0 to get P. Yeah, here. For uniaxial extensions, both sigma 22 and sigma 33 are 0. But if your rubber is loaded under, for instance, equibiaxial, where it is simultaneously stretched along direction 1 and 2, so sigma 11 and sigma 22 will be non-zero. It is only sigma 33 which will be 0. By P from sigma 33 equal to 0, not from sigma 22, because sigma 22 is not 0. I hope that's clear, yeah? Okay, the idea? Okay, so this is the end of this lecture 5. So I'd like now to move to, I can say this is a very quite special tutorial. It's quite different tutorial. I will open it here. Can you please, I have put it in my spectrum, okay? If you look at here, in the tutorial, so there is a special tutorial here. And then also you have data for the special tutorial. So can you please download the data for the special tutorial and also for the instructions for the special tutorial. So I will show the screen, my screen here to you. Yeah. Okay. I hope everyone follow, yeah? I will show you step by step how to do the treatment on Excel. And then I hope that you can do it at the same time. Because after that, you need to do summary of the result that you obtain and then send to me, submit to me as your assignment. If you have any questions, please let me know. Yeah. So if you follow closely one by one the step, immediately you can directly upload your assignment and it's done. You don't need to wait until tomorrow or 1 week to finish it. Okay. You just get the picture of the result and then put it in your slide. For instance, you just a simple slide, and then you send to me. Okay. Please let me know if you have questions. So here is identification of material parameters. Previously, I have mentioned in the very last slide that if you use Neo-Hookean, then there is one parameter which is C1 that you need to identify. If you are using Muni model, then there are two parameters, C1 and C2, that you have to identify from experiment. So what we are going to do here is to learn how actually the identifications of material parameters can be conducted, right? So here, I give the general context. For instance, as mechanical engineer, you need to design engine mounts. Engine mounts are example of components made of rubber. So the functions is to connect between the car engines to the car frame. Okay, and the idea is to isolate vibrations coming from the engines to the car frame, so that we as a passenger will not feel the vibrations of the engines. Okay. So because of the vibration of the engines, it means that the rubber is subjected to fluctuating loading. And then as it is fluctuating loading, it may lead to materials failure called as fatigue. Okay. Now, as mechanical engineer, in order for us later to predict failure, you need to be able to conduct stress strain analysis. For instance, using finite element software, such as you can use ANSYS or you can use Abacus. Okay, so in these situations, in order for you to be able to determine stress analysis, then you need to find the materials parameters. And then materials parameters can be obtained from the experiments. And this is where we are going to learn. So the objective here is that to identify materials parameters of rubber from two experimental data, uniaxial extensions and equibiaxial extension tests. So the Excel file that you have there contain the experimental result from uniaxial extension test and equibiaxial extension case. All right. So for this exercise, I'm going to focus only on uniaxial extensions and leave it the equibiaxial for you to do exercise for you to train at home. Okay. And then the assignment that I ask you to do is related only to uniaxial extensions, the thing that we are going to do here. I'm not going to ask you for equibiaxial extension, but please read and learn about it at home. Okay. So now, first, when you do stress analysis in finite element using ANSYS or using Abacus, you need to choose the materials model that you are going to use. Let's say that we choose to use Muni strain energy density. And we have learned that this is the expressions for Muni. Now, you have WC1 times I1 minus 3 plus C2 times I2 minus 3. So C1 and C2 are materials parameters that we need to identify. Okay, and then I1 and I2 are the two invariants of the left Cauchy-Green tensor given by this equation. So I1 is the trace B, I2 is this one. Things that we have discussed in the lecture. And then this expression for stress, you know it. We have seen it in the lecture. This is the general expressions. of the true stress, and then the engineering stress is related to true stress through this equation. This is we have seen in the slide before. Okay, now experimental data. You have two experimental data there. First is uniaxial extension. The second one is equibiaxial extension. Please read carefully. In uniaxial extension, the test is conducted on rubber band or rubber sheet having length, width, and thickness of 100, 10, and 10 mm respectively. And the tensile test, the uniaxial test, is conducted along the length, along 100 mm length. So the sheet is stretched along its length. Okay, so you have to know what are the cross sections. The cross section will be 10 times 10 mm square. I hope it is clear. Yeah, I repeat again. It means that the cross section of the sample is 10 mm times 10 mm. Now, the equibiaxial extension means that you simultaneously stretch the materials along two directions, for instance, 1 and 2, by the same amount. It is called as equibiaxial. If it is not the same amount, then we call it simply biaxial extension. If the two amounts are the same, we call it equibiaxial extension. So the geometry of the rubber sample is the length 100, the width is 100, and the thickness is 5 mm. So this rubber is stretched equally and simultaneously along the length and along the width, which means that the cross section is 100 times 5. That's the cross sections. Okay. So the experimental data are provided in a separate file. So please open the file. Okay. So if you look at the file, something that you will see is this one. Okay. Experimental data. So you have here the data uniaxial and equibiaxial. Equibiaxial, you can do it at home for you to do the practice. Okay. Uniaxial extensions, this is the elongations. Okay, elongation means that how the specimen length change. 0 means that there is no change of length, and then when we do uniaxial extensions, the length increases by this amount. Okay, and this is the load that we measure at each amount of elongations. You have this, and at the same time, this is equibiaxial, and this is for uniaxial and equibiaxial. Okay, so this is the original data that you have. I hope that you can open all. Yeah. So you will need to do it together with me here. Okay, next. Plot the experimental engineering. We will follow the instructions together. So I hope that you can also do it. Yeah. All of you are following, right?
Yeah.
Okay, please following. Because if you do it immediately, you will be able to submit the assignment. No need to wait again. Okay, you may need to do something else. You need to prepare for your slide, for your presentations, and so on and so forth later on. Now, let's focus on this. Let's do it together so that you have the result immediately, and then you can just send to me. Yeah. Okay. So plot the experimental engineering stress stretch curve corresponding to uniaxial extensions and equibiaxial extension respectively. Note that the stretch, which is lambda, is defined by the ratio between the current length L and the initial length L0. Okay, let's do it. I will guide you. Hope you do it also at the same time. This is the original one. Okay. And then let's say that because I want to focus on uniaxial extension, I can get rid this equibiaxial extension. So let's just simply copy this and open the new tab. Okay, just copy it. Let's say I will put it create a copy, and then don't forget to click create a copy. And okay, if I'm using old Microsoft Excel, yeah, so you may have much more advanced features, then the detail might be slightly different on how to do it. Yeah, so I have the original. I have the original copy number 2. Okay, let's say that this is I rename it simply exercise. Okay. Since I don't need equibiaxial extension, my screen is quite clear, right, for the Excel part.
Yeah.
All right. So in this exercise, I remove these two data because I will focus only on the uniaxial extensions. Okay. Now, This is the elongations. So what I need next is that from this data, because according to number 4, I need to plot the experimental engineering stress and stretch. Stretch means lambda. Okay, so I need to find first. You can find directly lambda, but let me just do it gradually. Strain. This is strain. Okay. How to get strain? Strain is delta L over L0. Okay, so which means that what is delta L? Delta L is elongations. What is L0? The length is 100. If you remember, see here, the length of the sample is 100. Okay, so that now the strain is simply delta L over L, which means that I simply put a simple formula that the strain is delta L, and delta L is elongations divided by 100. Get this one, okay? And then I need to repeat the process for all value of elongations to get the strain. So what I do is that just simply, if you look at in the corner here, you double click, okay, the point in the corner until it becomes black, the plus note there, and then just double click. So you get everything all the way until the data here. Yeah. Everyone can follow, yeah? Okay, everyone can follow. It's a very simple. Sorry, everything okay, yeah?
Yes, doctor.
Okay, this is just a simple Excel treatment. This is strain. Okay, I need because later I need stretch curve. Stretch is lambda, yeah. So I put this is stretch, or call it also lambda. So I have two names there, yeah. Just to remind you. So what is lambda? Remember that lambda is L over L0, and L is L0 plus delta L, which means that lambda is simply 1 plus epsilon, 1 plus strain. So this means that in order to get lambda, I just simply 1 plus strain, which is here. So when strain equal to 0, lambda is equal to 1. And then I repeat the process for the whole value of strain to get the corresponding lambda. Then I get the value of lambda. I hope everyone follow this one, yeah? Very simple. And then next, I need to get the engineering stress. So I just simply increase the size of the column. Okay. Here is, let's say, engineering stress. Well, I can put stress. What is engineering stress? Engineering stress is force over cross-section. So the stress, I want to make it in megapascal. This is easier. Okay. Okay, what is the stress? Is force, which is load over cross sections. The load is here in the column B. Okay. What is the cross sections? I have mentioned earlier. Here it is given the informations. Because the rubber band is stretched along the length, and the length is 100 mm, so the cross section is 10 times 10, so 100 mm square. Okay, so now means that force over cross sections, the force is this one in Newton divided by cross section in millimeter. So directly, if you divide Newton over millimeter square, you get directly megapascal. So this is convenient. I just simply divide it by 100, which is 10 times 10. Yeah, and have this value. When the strain is 0 or lambda equal to 1, then the stress is 0. Okay, I do repeat this process for the whole value of load. I get this one. So now you just simply need to plot stress as functions of lambda, and you know how to do it, right? So simply do this, and then you just simply drag all the way the whole data there, and then you create chart. Let's do it with just line, smooth line, and this is what you have. This is the stretch, the lambda, sorry. Here is the graph. I hope everyone can get it, yeah? So the graph starts from lambda equal to 1. So I will not give a detail. So you need to update. This is give the label here. This is lambda. This is engineering stress. I'll leave it to you when you do the report. Yeah. So now, well, because it is starting from 1, I think we can also choose to start the axis from 1. Okay, like this. That's the minimum equal to 1 is equal to 0. So I have this one now. So this is the engineering stress and strain. So sorry, engineering stress versus lambda. So we can put, for instance, format, chart layout, sorry, axis level. So horizontal, we keep title, and the title, for instance, this is lambda or bracket stretch. Okay. I will increase the size for you to make it clearer, and then the size of this one also I will increase. This is 14, for instance, and then for another formatting is that to have axis along vertical axis. Well, you can do it, and this is we put, sorry. So this is engineering stress in megapascal. Which I can increase also the font, make it, for instance, 14. Okay, so this is the engineering stress and lambda curve. Okay, experimental one. Okay, so as you see, this is the rubber when it is stretched, and then after that it goes up rapidly. Okay, so we did already number 5.1. Okay, is everyone follow for this one so far?
Yeah.
Okay, good. All right. So next is 5.2. Derive the theoretical expressions of engineering stress P as a function of stretch for incompressible hyperplastic materials under uniaxial extensions and equiaxial extension respectively. So we do not do for equiaxial, but the process will be the same. Let's do for uniaxial extensions. And then we need to put them in the following form, which is this one. 2 times lambda minus 1 over lambda m plus this one. Okay, where m and n are positive or negative integer. Right. First, we need to derive this one. We have done it in the lecture just now, but I will go back and put things in detail to have a look quickly. Okay. This one. I'll go up. Okay. Here. So this is the case. Okay. This is, I repeat what we have seen just now in the lecture, but a bit more detail. Uniaxial extensions, this is F, this is B, and this is I1. Okay. Next, this is the equations, and this for through stress, this is the equations for engineering stress. And then as I have done in the lecture, I put in the matrix form, all this one, putting 0, 0 in sigma 1, 1 and sigma 2, 2 directly, because we know they are 0. So that if I take out only sigma 1, 1, because sigma 1, 1 is the only non-zero component, so sigma 1, 1 is simply minus P plus these terms times this, minus these terms times this. So, W, we know that in this exercise, we choose W Muni, depends on I1 and I2, so we have it. Okay, lambda, fine, we have it. We stretch from certain value. We have the value of lambda just now. We don't know the value of P. So we need to identify that. Here, how we do it. So P can be determined from the fact that sigma 3 equal to 0 or sigma 2 in this case. Okay, sigma 3. So what is sigma 3? Sigma 3 equal to 0. If you look at this one, 0 equal to this one plus this one terms times 1 over lambda minus these terms times 1 lambda square, which means that if I move to P, so P is given this one. I hope it is clear, yeah? So that if I insert back the expressions of P into sigma 11 here, I get this one. So sigma 11 equal to 2 times this, the whole P here, and then I have all the terms here. So I have this one. Just rearrange, all right? Because this terms is the same, so I can just group it. This is lambda square, and this is 1 over lambda. So I just simply insert it. Again, I remind you that I1 equal to trace B, which in this case is lambda square plus 2 over lambda. Now, how to get the final expression? So this is the step. I will go quickly here, so make sure that you follow, yeah? Here, I go back. We still have the terms I1. So we need to expand this I1. And I1 is this one. So which means that now, next, is that when I expand I1, I1 is this one. I insert, this is I1. So this is the whole equation that I had before. The difference is that I insert now I1 here in the bracket. And now I expand the equations. Okay? So I have this. The first term here, 2 times this one times the terms here, so which is this one. I expand and then this one, the second terms, and then the rest remains the same here, the third one. Okay, and then after that, I make further expansions of these two brackets here. The rest remains the same. Okay, so the first terms here remains the same as the previous line. These terms I expanded. Okay, and then the third terms here remains the same as on top here. Okay, and after that, I make necessary arrangements. So this is differentiation W with respect to I2, similar like this. So I can make simplifications. This is lambda 4. This is minus lambda 4. So I can get rid this lambda to the power of 4. So it is gone. Okay, and then I still have lambda, which I put it here below. And then I also have terms, which is this is minus 2 over lambda square. And then here is minus minus become plus. It is 1 lambda square. So I have these terms. So these last two terms, I simplified and get these expressions. The first terms remains the same as before. This one and this one. Okay. So the first terms, again, I keep it. The second terms, I modify slightly the expressions by taking out 1 over lambda and then modify the terms in the bracket to become this one, so that this bracket will be the same with this bracket, the terms inside. Okay, so this bracket, the terms inside this bracket is the same as the terms inside this bracket. So by doing so, I can then take out this lambda square minus 1 over lambda, this one, and I have the remaining expression here. So this is how sigma 11 is obtained that I show you in the lecture before. Is there any question so far? Can everyone follow this one?
Yes, okay.
Okay, good. All right, good. Clear, yeah? So next is that this is sigma 11 that I obtained. This is the true stress. How about the engineering stress? Well, the matrix engineering stress can be obtained from this. So go back to the matrix. So this is the matrix of P, engineering stress, okay? And then equal to 2 stress, which is also all 0 except in one component. And then what is F? Well, F minus transpose is this one, okay? So you get the F, and then you do the inverse, and after that you do the transpose. Or you get the F and do the transpose and go inverse. The order is not a problem, okay? So when we do that, then I have the final expressions for the matrix for engineering stress. So which means that the engineering stress is simply true stress over lambda. So this one, if you divided all these terms here by lambda, then I get P11. P11, sigma 11 over lambda, and it is equal to this one. All right. So now, looking at the form that we have in in the tutorial, I have to put it in this form. Okay, so because why? Because we choose Mooney equations, so the differentiations of W with respect to I1 is C1, and this is 1 over lambda, I keep it here, and differentiations of W with respect to I2 is C2. This is clear, yeah? And then, by comparing with the general form that I have in the tutorial, then we get immediately that M equal to 2 and N equal to -1. Is that clear?
I think
Okay, is there any mistake calculations? Tak ada ya? Alright, so this is how we write the equations in the form as requested in the tutorial. So we know that M equal to 2, N equal to 1. Okay, I finished there, which means that I finished already this number to derive and then to put in this form. We know that M equal to 2 and N is equal to -1. Please take note. Okay, so we know now that if we put in these equations, we can put it in the linear form, theoretically, yeah, these equations, to put it in general form of y equal to C2x plus C1. This is a linear equations, yeah, y as a function of x, where C2 and C1 are the constant. And then when we put in this way, it means that y is actually p over 2 times the terms in the bracket. So if we put this on the other side, so I get y, and x is basically lambda to the power of n. Is that clear? Can you all follow? Why? Anyone would like me to repeat? Please let me know. Yeah.
can I repeat?
Okay, sure. So this is the original equations. Okay. So now, let's say that the left terms is divided by 2 over times in the bracket here. So the terms is gone, divided by this one. So I have these equations that P over 2 times this is equal to C2x plus C1, where x is equal to lambda to the power of n. You agree? I can change these equations to become this form, y equal to C2x plus C1, where y is equal to this one, and x equal to lambda to the power of n. Do you agree?
Alright.
Boleh ya? So x is simply lambda to the power of n. So y is p divided by 2 times the terms in the bracket here. Okay. So now we know that these theoretical equations can be put in this form, which is linear form. Okay. Now the idea is that we need to find C1 and C2 from the experimental data. That's the whole idea. If we look at these theoretical equations, it means that if in Excel we can plot y as a function of x, and then plot the experimental data, and then after that get the trend line using linear equation, then we get the slope, we get the constant C1, and this value correspond to C2 and C1. Do you understand the idea? Yeah. So how to get C2 and C10? Simply plot the experimental data following this form, y is functions of x, and then it should be linear line. If it is linear line, then the slope C2, the C2 can be obtained from the slope, and C1 can be obtained from the intercept with y-axis. Let's do it. Number 3. For uniaxial extension and cubic extension, plot the experimental value of y as a function of x. That's what we are going to do now. Let's go back to our Excel file. Okay, go back to Excel file. We need to plot y as a function of x. Now, okay, let's see first x. X is lambda to the power of n. Lambda to the power of n is actually 1 over lambda. All right, so let me check what I have done before. X, okay, I need to, okay, now here, I need to get X. This is value X. What is X? X is lambda to the power of n. And the value of n is -1. So it is 1 over lambda. So this one is simply equal to 1 over lambda. Where is lambda? It is on the left here. Like this. So I do all repeat, click the corner here, double click, and I have all the value of X. Right? So I hope all of you follow, yeah? X. Any of you get a problem to get this value? Maybe I need to increase the size here so that you can see more easily. 125%. Okay, I hope that one is clearer, yeah? Maybe I can put it to 150, which is still convenient. Okay. Is it clear? Okay, X. All of you get X, right? Managed to get X.
So just a question.
Sorry?
X is 1 over lambda, right?
Betul. So I will write also here, X equal to 1 over lambda. I think it's clear, yeah? So we have lambda here. So this one is equal 1 over D6, and D6 is lambda. Yeah. Okay? All right. Okay. Next. Next is I need to, what is X is, and then Y is this one. So I need to plot this one. P is engineering stress over these terms. Okay. Okay. So what I will do is that instead of doing all at one step to minimize the error, I will just simply calculate first what is the terms below here, the divider here. Okay. The 2 times things in the brackets. Let's calculate that one. Okay. 2 times lambda minus 1 over lambda to the power of m, where m is equal to 2. We have find it. Okay. So lambda minus 1 over lambda square. Okay, let's do that. Okay. Here, let me call it as the divider. Okay. The divider is 2 times, in the bracket, lambda is this one, minus 1 over lambda square. Close. Okay. So the divider is 0 for lambda equal to 1. So I do the process all the way below here. Can everyone get this one?
Yes, Doctor.
Okay, good. Not difficult, yeah? Okay, I have the divider now. So in order for me, go back here, in order for me to get the value of y, I just simply P divided by divider. Okay, so P is the engineering stress. So here is y, the value of y. I have it here. So this is y equal to P divided by divider. So equal to what? Where is P? P is, well, the stress here, divided by divider. This one. Oh, it's not defined because division by 0. It's fine. Ignore it first. Okay. We know that the terms below here is 0. So just repeat the calculations for everything here. Now what you need to do is, can you plot y as a function of x? Let's put the chart again, the new chart, which is again in the form of, I think, let's do it in line like this. Okay, I haven't decided on, I haven't put the value of the x. This is the value of y. So I need to edit the graph. Again, detail depends on the versions of your Excel, Microsoft Excel. Yeah, the x value is the value of. Okay, I need to hear where is the x. This is, oh, this is the x here, all the way until f bawah, below here, which is this one. So I said okay. Then I get the plot, which is this one. You should get something similar to this one. Let me know. Do you get something similar? Okay, everyone managed to get the graph? Let me know.
Doctor, can you please repeat how you get
Sorry, you
the
did not manage. Which one is it? Okay, first thing first, did you manage to get all the value of x like this?
Yes.
Okay, you managed to get the similar value for y.
Yes.
Okay, good. Now it's just a problem of plotting the data, right?
Yes.
Okay, so what is your difficulty? You do not get the curve.
Yeah.
Okay, you can put it in your you can do it in your select data.
Oh, all right.
Select data, right click and select data, and then it is in your x value. So you need to drag the value of your x from the beginning until the end. Okay, and let's see whether you get the same thing.
Oh, okay, get it, sir.
All right, good. For others, do you have any problem? Please make sure you do it, yeah, because at the end, if you do it, you do not need to repeat it sometimes later. Just do it, and after you do it, you can immediately submit to Spectrum for your assignment.
Doctor, can I see the formula for the denominator for
the divider, denominator here?
Yeah.
Is it this one? Okay, this is 2 times lambda minus 1 over lambda square. Is it something that you would like to see? The equation which is here, yeah? Here. Hadi, you managed to do it?
Yes, sir.
Okay, good. You managed to get this graph, yeah? Okay, now, if we see here, this is the graph, this is the shape. Okay, this is, okay, let me put the label of the table of, hold on here, to make things clear for all of us. Okay, and then I would chart layout, and then I will put label to horizontal axis below here. What is the horizontal axis? Horizontal axis is x, the quantity that we call as x. What is in the vertical axis? It is a quantity that we call as y. Okay, so this is y as a function of x. Okay, so there is a small problem here because there is a value divided by 0 and it is undefined. So what we can do is that get rid that point because it does not define. So what should we do here? You just simply remove the point 1 by look at the corner here until the pointer becomes small box like that. Click and then just remove 1 point there. So you remove the value which is just now going down. I repeat again. Okay. Oops. Where is it? Okay. All right. So again here, I want to get rid the not defined quantity. So I just simply remove it. Yeah, remove it here. So I do not include this first point in the graph. If we do that, then you can remove the part which is go down below here. Can all of you do this? Manage, yeah, you do it. Everyone? I only hear Nurul and then Hadi. What about the rest?
Yes, doctor.
Okay, yeah? So, all right, good. So now, going back to this one, to the tutorial. When we plot y as a function of x, according to the theory, it should be a linear equations. But when we do it to experimental data, it is not really linear. It is a curve here. Okay, so it's fine because the theory is simply based on the model, and this one is the real one. So now, how do we get C1 and C2 then from this? Because theoretically it has to be linear. So what we need to do is that we need to find C2 correspond to the slope and C1 correspond to the intercept with y-axis. How to do that in Excel? We just include the trend line. Okay, you click the data there, and then to insert the trend line, right click. You have, depending on the versions of your Excel, you put add trend line and choose linear line. Okay, and then in the options, put display equation on the chart because we need the equations. Okay, so this is the equation that I obtained. So I will make it slightly larger, put it here, probably. Bold in red, size 12, make it clear. So the slope is 0.3394. The intercept is this one. Can all of you get more or less similar?
Yes, doctor.
Okay, good. All right, you get. So which means that now immediately you get the slope. What is the slope? C2. Okay, you get the value of C2. It means that C2 equal to 0.3394. What is C1? C1 is the intercept with this one, which is 0.420. Okay, yeah. So we get the value. This is how you identify the materials parameters. Next is that let's compare the predictions according to Mooney model with the experimental data. And how to do that? Okay, what we need to do is that going back to this. So we have done number 3. Okay, we have done number 4 here. 5.3 and 5.4 we have done. You can do exactly the same thing for equibiaxial extensions. What is the difference when you do it in equibiaxial extensions? It is the F is different. When the F is different, then you calculate B. B will be different. When you calculate B different, then I1 will also be different. And then and after that, your expression of the stress, the Lagrange multiplier that you need to identify is coming from sigma 33 equal to 0. It will be different. Okay, the step remains the same. The exact value will remain the same. The exact step will be the same, but the value will be different. For instance, M and N for equiaxial will be different from uniaxial extension. All right, we've done number 3, we've done number 4. Now let's do the comparisons. Plot the theoretical engineering stress stretch curve using the Mooney model that we just obtained, C1 and C2 we just obtained here, and compare with experiment. All right, how to do that? Now we need to come back to the final equations, which is this one. I need to go back to this one, I think. Back to this. So this is the theoretical engineering stress. 2 times lambda minus 1 over lambda square. Which lambda I should use? You have the value of lambda in the Excel file. So we calculate based on that lambda. What is the value of C1? We get it just now. What is the value of C2? We get it just now. We just simply replot again theoretical engineering stress according to these equations. So let's do it together. Okay. Again, because this is equations consists of two parts. The first part is 2 times in the bracket. The second part is this one. So I will divide into two terms, sorry, the first terms and the second terms to make the calculation easier so that we avoid any potential error in our Excel calculations. So I'm going back to here. So I will have term 1 and term 2. Let me check what I have done before. Terms, okay. So I have here term 1. I have term 2. Okay. Let me go to here. Okay. What is term 1? My term 1 is, oops, this is this one, 2 times lambda minus 1 over lambda square. Then let's do it. So this one is 2, equal to 2 times, in the bracket, lambda. Where is lambda? I have lambda here. Lambda minus 1 over lambda square. And then close the bracket. And I have it, the first term, 0. Do exactly the same thing for the rest. Double click the corner and you get all the rest. What is the second terms? Well, the second terms is C1 plus C2 over lambda. Well, what is C1? C1 is, this is where is the C1 actually? C1 is, okay, C1 is this one. So C1 is 0.4. Yeah, C1 is 0.4. Hold on. It's linear. C1 is the 0.4. This is C1, 0.4. C2 is 0.3. So the second terms is C1 plus C2 over lambda. So it is equal to C1, which is 0.4024 plus C2, which is 0.339 divided by lambda. I hope I'm doing it right. 0.44, okay, 4.3, okay. And then I double click and get term 2. So now I have the theoretical stress. Theoretical stress is the product of term 1 times term 2. Okay, so here is, okay, the theoretical stress. So what I need is that with this lambda, I just keep the, with this value of stress, with this value, done. What is it? I have questions in the chat box. Let me check first. Can I straight put terms 1 is divider? Yes, yes, correct. You're right. Correct, yes. But don't forget. Yes, of course. Yes. You're right. Any other questions, Hadi?
Doctor, can I see the second term equation in the Excel?
Sure, I can. So Andre, it's okay, yeah. You can directly, term 1 is actually equal to divider. You're right. And then okay, this is Hadi just requested for this one, right? The equations. So it is C1 plus C2 over lambda. Okay, is that clear, Hadi?
Doctor, it's 0.39 or KK9?
Sorry?
The value for
The value is 0.592.
0.3394. Oh, yeah, you can put 4. Yes, we're right. Is it this one?
Yeah, yes, Doctor.
Yes, okay, correct. Yes, right. Thank you. So we have theoretical stress. What we have to do now is that plot. This is the first stress here is the experimental stress, and this one is the theoretical stress. Now let's compare. Then let's just simply plot, which means that just now I have already plot this one, yeah, engineering stress. So I bring back this. So the blue, basically, if I click here, I know that this is engineering stress. So let me edit this one. Just right click and then select data and then put in the name of the series, this is experiment. Okay, so this is the experiment. I need now to add 4. Maybe I need to reduce slightly the size so that you can see easily. Okay, I will remove this part to the left. So this is the experiment. So the experiment is you plot stress with lambda. You have to add another graph, which is theoretical stress with lambda. And you can easily do that. Again, right click, select data, and then you simply add the second series, which I put the name theoretical stress. Okay. And then the x value, the same like before, we use lambda. The x value is the lambda. So I put from here all the way until the last one, which is here. So I have it. And then for y, I insert the value of theoretical stress, which is this one, all the way until this one. Okay. I have this. Do you manage to get this result? So please see. Okay. Can anyone get this? Let me know. Is everything all right?
Hold on,
Boleh dapat? So those who manage to do it, please write in the chat box, yeah. Okay, can I have a feedback? Do you manage to do it?
Yes, Doctor.
Okay, okay. Arunesh, you managed to do it. Well done.
Yes, everything okay.
Okay, good. Hadi, okay. And then Nurul, okay, Nurul. Dipanraj, okay, good. Well done. Okay, the theoretical stress, it means that this is the stress that is calculated theoretically based on the model Mooney, which means that these equations, this is the theoretical stress, yeah, that we derive according to the model, which is the model Mooney. Is that answering your questions, Andre? Okay, great. All right. Any other questions? Okay, so basically this is how we do the identifications of materials parameter. So as you can see, if I go back to the Excel file that I have, so the blue line is the experimental data, and then the red line is the one that we obtain, the prediction that we obtain by using Mooney model. Okay, as you can see here, if the lambda is not high, 1.2, for instance, 1.2 means that actually the strain is 20% strain. So you can use Mooney model satisfactorily, okay? Slightly higher than that, well, there is slight discrepancy, but still okay. You still can use Mooney, okay? But once you reach value more than lambda equal to 2, lambda equal to 2 means that it is 100% strain, then you really see the discrepancy between experiment and theory, which means that the model is only capable to describe more or less correctly the stress strain characteristic up to only about less than 2, lambda less than 2. Beyond lambda equal to 2, you need to use other model. Mooney cannot be used anymore. If the components that you are dealing with undergo strain which is less than 100%, well, Mooney is okay, you can use it. Okay, but if it is other than, if it is more than 2, then you need to find other model to simulate. Okay, so in this example, I give you a case where the parameters of materials can be determined using a simple identification process using Excel. This is how the idea do it. You just compare between experiments and the theory to find, well, you fit with the experiment to get the parameters C1 and C2. For other models which involve more than 2 parameters, there are models with 3 parameters, C1, C2, C3, or others models, series which is long. How we get it? There is a systematic algorithm for identification of materials parameters that we do not learn here. But the idea is that these parameters are fit from experimental data. You need experimental data so that you can fit and get the parameters. And once you get the parameters, then you can do the stress analysis. That's the whole idea. Yeah. So with these models, again, you can do the predictions as long as the stress, well, the strain is, well, the lambda is less than 2, moderate strain. All right. So as you can see, I'm going back to this one special tutorial. So starting from F, and you get B here. Okay, if I run again, and then after that you get I1, and after that you write the equation for the stress, and then you have to identify what is P, and then P can be identified from sigma 33 equal to 0. You get the value of P, insert back sigma 11, do the proper differentiation, and you get the final expression here. How about equibiaxial extensions? Okay, the process remains the same, but you will have different F. So in the case of equibiaxial, it will be lambda. This is also lambda because it is the same amount, and the rest is 1 over lambda square, because the product of lambda 1 times lambda 2 times lambda 3 must be equal to 1. It is incompressible. And then with this value of F, you need to calculate B, you need to calculate I1, and then the process follow exactly the same thing. And the P is determined from sigma 33 equal to 0 also. So all these process are the same, but the detailed equations will be slightly different. So you will end up with finding that for the case equibiaxial extensions, the value of m and n will be other values, which will differ. Okay, so you do exactly the same thing with the Excel file, and then you can finally get the similar comparison for the case of equibiaxial extension. Noting that in equibiaxial extension there will be engineering stress 1,1, engineering stress 2,2, but the value will be the same because it is equibiaxial. All right. So any other questions? I stop here.
What kind of thing that we have to do?
Clear, yeah?
Doctor, what time do we submit in this bed?
Okay, what it is the report? Yeah, what I want in the report is that can you just submit the Excel file that you have, this one, with the proper graph. Okay, that's it. You send to me, and that is the assignment that I request you to do. Is that answering your questions, Hadi?
So the report just the Excel file only.
Just the Excel file. So, but I want you to have a proper graph, yeah, with the proper notions here and so on. Just put in this raw data is okay with the graph. So I will check from the graph. That's your assignment.
Doctor,
Okay.
we have to do the equibiaxial also.
In the report, no need. No need.
Oh,
Only this that we have done.
okay.
All right. So it's a simple one. So if I mentioned, if you just did it just now, you only need to update just the graph to make it nicely, and then you get the result. Okay. So you can submit. I will open now the submission link that you can submit. So submit now if you have it already, so you can focus on your preparation for FYP presentation and so on and so forth. It will not be burdening you. If not, I will still give you times until Friday next week to submit. Don't worry. But if you manage to do it just now, just with the touch up of your graph, just send it to me. I want to see your raw data, how you do it. Is that clear for everyone?
Yes.
Okay, so for next week, as I mentioned, I will upload the lecture for the lecture number. The next lecture is number 6. Yeah, I will record it and put it in the Google Drive. For next week, what I'm going to do is there's a simple. It will not be a lecture, but a simple discussions about the preparation for your final exam. Will it be okay? Yeah. Which day is your presentation for FYP?
It should be Monday to Wednesday.
Monday to Wednesday, yeah. So there is no issue for you to attend the Thursday. It will not be a lecture, heavy lecture. I will just open opportunity for you if you have any questions, if you have things that you would like to clarify for the preparation of your final exam. All right. So again, this is the end of the lecture 5 with this assignment. I will open the assignment link all the way until Friday next week. Okay, that you have to submit. I strongly suggest you to submit soon because we have done it basically just now. And then lecture 6, I will record a video and I will put it. And then next week will be the last sessions. Is only for discussions. Discussions only. If you have a questions, I'm open. I give opportunity for the discussions for your preparations on your final exams. Right? Okay, I think that's all for me. Is there any other question before I close the session?
Doctor, for previous week, the record will be in the drive.
Yes, I actually have uploaded everything in the drive. Do you have any problem in getting the file?
I still not get the January file.
Oh, January, because last week we don't have class. Our last class in December, remember? Because last week I had to cancel the class.
Oh, okay. Okay.
So the last class, if I'm not mistaken, is on the 24th of December.
Okay. Thank you, Doctor.
Is correct? Yeah?
This
So
class will be uploaded.
of course, for this class also I will upload to the systems, and then I will record another lecture for lecture 6. Okay, also in the Google Drive, and then for next week it will be a short, a simple. It's not a lecture. It's just a session for discussions if you have questions for your final exam. Okay.
Thank you, Doctor.
All right. Thank you, Wael. And then who are other questions? Any other questions before we stop? Okay, no questions. So thank you very much. So I will see you then next week for just a final short discussions, open sessions for the preparations of final exam. Yeah. Okay, thank you very much. I will immediately open the link for submissions for this exercise. So please submit it. I will open until Friday next week. Yeah. Okay. All right. Then I will see you next week. Bye.
Thank you, Doctor.
Thank you, Doctor.
Okay.